First, we're going to look at the process of simulating the operation of an NFA. And in order to do that, we have to look at the representation. For state names, we're just going to use the integers from 0 to m, and those are just indexes into the regular expression string with one extra one for the except state. So if the RE has m characters, we've got m plus 1 states. And then we've got the match transitions. We'll just keep the regular expression in an array, and then for characters that are not meta characters, that are just characters from the alphabet, there's a match transition just to the next element, just add 1. So that's an implicit representation of the match transitions. And then the next thing is the epsilon transitions. So since there might be multiple edges leaving from any given state, and it's directed, it always says go from this state to another one, we'll use a directed graph. So we just have a bunch of edges with given vertex names. And that's convenient. That's what we use for our graph processing algorithms, was indexes for vertex names. So this is totally well suited to building a digraph using the basic digraph processing methods that we talked about when doing graph processing. So that's the representation, and then given that representation, it's very straightforward to find out for any state what are the possible next states. If it's got a character, the possible next state is to match the character and go up 1. Otherwise, it's the vertices that are pointed to by the edges in its adjacency list. Those are the epsilon transitions. So let's take a look at, just given that basic idea that we can always get to the transitions from any given state, how we're going to do a simulation. And so the idea is summarized by this diagram here. What we're going to do is, at every step, each text character that the machine does read, we're going to keep track of the set of all possible states where the NFA could be after reading in the I text characters. So say we've done that. This is just a schematic. So there's a bunch of states that we could get to after reading I characters. Now, in some of those states, they are labeled with characters, and if that character matches our text character, they can take us to another state. So say in this case there's 3 of them that matches, and the other one has a meta character or a different character, and it couldn't take us to another state. So that gives us all the possible states that you could be in just after reading the I plus first symbol. And then what we do is take a look at the possible null transitions that we could go to from those states, and that might take us to lots of other states. But that's all the machine could do. It could read a character, and then it can take a bunch of null transitions, but that's all it knows how to do, and that'll give us all the possible states that it could be in after reading I plus 1 symbols. And then we just continue in that from every one of those states. Some of them match the character, and then look at all the epsilon transitions. So that's the basic idea, is to simply keep track of all possible states the NFA could be in after reading the first I text characters. The only thing that's complicated is how do we get all the states that we could reach by epsilon transitions. And we'll look at that in just a second. It's actually very straightforward. But let's look at a demo first. So this is our machine for A star B or AC followed by D, and let's suppose it has this input. So let's do this demo. Okay, so we're going to check if the input matches the pattern. We're going to start the machine in state 0. And so the zeros, the states you could reach from the start, And then now we want to get to all the states that you could reach by epsilon transitions from the start. And so there's a bunch of them. So we could go to 1, and from 1 we could either go to 2 or 6. From 2 we could go to 3. From 3 we could go to 2 or 4. So we could get to all of those places from the start without scanning a single character. So 0, 1, 2, 3, 4, and 6. The machine could be in any one of those states before it scans a single character. So that's where it could be after 0 characters. But what about now after the first character? Well, out of those states, only 2 and 6 involve matching an A. So the only thing that could happen next, the machine could do next, is to read the A in either state 2 or state 6. And those are going to be match transitions. So in the first case it goes to 3, and in the second case it goes to 7. So the set of states that could be reachable just after matching the A is just 3 and 7. But now from those states, it might get somewhere with epsilon transitions. We have to look at the epsilon transition graph. And what states could it go to from epsilon transitions from these two? Well, from 7 is nowhere to go, and from 3 it can go either to 2 or 4. From 2 it could go back to 3. So the total number of states that it could be after matching A is 2, 3, 4, and 7. And so that's one step. We've matched one character, and we have kept track of all possible states the machine could be in after matching that character. Now what about the next character? You see these 4 states take us all different ways. You could have an A, a B, or a C next, and it could get somewhere. But it happens we have an A, and the only one of these states that matches an A is 2. So after matching the second A, the only place it could get to is 3. And so that now we have only one state to work with, but where could we get with via epsilon transitions from 3? And so, well, you can go from 3 to 4 or 2. Well, we did this before, and then from 2 back to 3. So we could be in 2, 3, or 4 after matching 2 A's. So that's all the possible states we could be in after matching the 2 A's. Now what's next is the B. Only state 4 matches the B. So the only place we could be right after matching the B is in state 5. And that's after matching the B. Now what about epsilon transitions? Well, state 5 has an epsilon transition to state 8. So we could take that one, and 8's got one to 9. So it could be in either 5, 8, or 9 after matching AAB and then following all the epsilon transitions. But it's really important to keep in mind there's no other state the machine could be in. It doesn't have any other way to get to, after matching AAB, it couldn't get to state 7 or 6 or 2. Those are the only possible states it could be in. And since we're each time progressing through the input, we're making progress to the end for sure. So now to finish up this example, the only state out of those 3 that matches D is state 9. And so that's a match transition that reads the D. And the only place you could be after matching AABD is state 10. And then now we follow epsilon transitions. And that epsilon transition could take us to 11. So the only place the machine could be after matching AABD is 10 or 11. Now our condition on whether we accept a string or not is whether we could get to the accept state, and in this case we could. It is possible for the machine to get from 0 to the accept state and read all the input characters, so that simulation is a proof that the machine accepts the input AABD. We simulated its operation all possible ways, and we managed to find the accept state. Of course, if we had tried some input that the machine doesn't recognize, we'd get stuck somewhere and either not get through the input or have no possible states it could be in. And that would be a proof that it does not accept, since we try all possibilities. So the only thing that's complicated in this computation is reachability, but actually from our study of digraphs, this is one of the simplest problems that we discussed. What we really discussed was single source reachability, that is, given a source, can you find all vertices that are reachable from that source? And that was depth first search. So we had very simple depth first search. But also in that API, we put vertices reachable from a set of sources, so an iterable of sources. And so can we get what we really need is all vertices reachable from a given source from a source set of vertices. And it's easy using DFS. You just run it from each of the sources and you don't unmark the ones that you get to. And that stops DFS from revisiting any vertices, and it marks all the vertices that you get to from that set. So it's just a simple extension of our DFS implementation. It's going to run in time proportional to the number of edges plus the number of vertices in the digraph, and it's a very simple computation, digraph reachability. So given that capability, which we discussed in graph processing, the implementation of the NFA simulation is very straightforward. So this is a data type that implements the NFA. So we have a constructor that takes a regular expression as its argument, and it's going to build the NFA, and it's got a method to build the digraph that we'll talk about later, but it's also got a client method recognizes where the client can, after the NFA is constructed, it can take a text string and return true or false by simulating the operation. So we'll take a look at the building the digraph in a second, but the one that we're talking about now is simulating the operation of the NFA once it's built for a given text string. And this is the complete code, and it expresses in code what we talked about in English during the demo. Is amazingly compact implementation of this idea of simulating the operation of an NFA. So we keep a bag of integers or set of integers called PC. That's kind of like program counter. So that's the set of all possible states that the NFA could be in. And we build a DFS from our epsilon transition graph. So the first thing that we do is do we put onto the PC all the states that you could get to from state 0. So that's build a DFS that marks all the states you could get to from state 0, and then go through and put all of those states onto the PC. So that's our starting point, is all the places that you get to via epsilon transitions from state 0. So now during the execution of this for loop, PC is the thing that we have, all the states that you could reach after scanning past the ith character. So we initialize for the 0th character. And then all we do is, for every one of those states, well, first thing we do is test if we reach the accept state. If we reach the accept state, we're going to have nothing, we're going to claim we have nothing left to do. If we have a match, that is, if the character in the RE at that state position matches our ith text character, then we're going to keep another set of possible states called match. So those are the ones you could get to just after matching a text character. And so we'll just add v plus 1. So if we find a matching character at v, we just go to v plus 1. That's the implicit match transition. And here we'll throw in don't care because it's so easy to do. If the regular expression says I don't care what character matches, then I'll throw that one in too. This just adds don't care to the implementation. And so we do that for all states in our PC, and the states that we could be in just while looking at the ith character. If we have a match, then we put the next states into match. So now what we have to do is follow the epsilon transitions from match. So now we build another DFS, which gives us marks all the states that you could reach by starting with any of the states in match. And now we'll rebuild a new PC. We'll just set BC to a new bag and put all the marked states for that search. So those are all the ones that you could get to via epsilon transitions right after a match and put that in the PC. Now we have a new PC, and we've read the ith character, and we go to the I plus first character and simply continue. So when we're done with all of the text, then we can test if we made it to the accept state. That is, if any of the states in our current set of states is the accept state, we return true. And if we didn't get to the accept state, after all of that, we return false. Very compact code that takes advantage of our implementation of reachability for digraphs in a reasonable way to simulate the operation of an NFA by keeping track of all reachable states. What about the analysis? Well, it's easy to see that not difficult to see that if our text is n characters and we have an m character pattern, the worst that could happen is that we take time proportional to m times n. And that's just because for every one of the characters, we have a set of states, a set of all possible states, and we iterate through that set of possible states a few times. We even run DFS on it, but that's linear. And there's the extra point that the number of edges that we have is less than 3m. No node has more than 3 edges leaving it. The total amount of time for each character is proportional to m, and there's n characters, so the running time is proportional to m times n. So that's the cost of the simulation. Of course, a lot of times the size of the set of the states is much smaller than that. So in many real-world problems, it's closer to linear. That's an NFA simulation.